Hello, my name is Minhae Kwon. In this video, I'm going to talk about distributed topology design for network coding deployed large-scale sensor networks. For this work, I have worked with Professor Hyunggon Park. In this presentation, I'm going to start with introduction, then move to problem formulation. Next, I'm going to talk about proposed solution called the network formation game, then move to simulation research. Lastly, I will finish this presentation with conclusion. These days we are living in a connected world. The number of connected devices is increasing, and it allows anybody to be connected at any time and anywhere. Moreover, recent devices are now able to instantaneously form large-scale ad hoc networks by making connections among them. For example, there are mesh networking platforms such as Bluetooth Low Energy Mesh and Qualcomm Wi-Fi self-organizing network. Therefore, we need a solution to topology design. However, there are emerging challenges. Firstly, since now we need to consider a large number of devices, it is too complicated to decide how to make connections between devices. Hence, it's better to find a distributed solution with low complexity. Secondly, because emerging networks have multiple sources and multiple destinations, there are multi-source multicast flows. But this may cause data paths to be frequently overlapped in network, so that bottleneck problem becomes critical in such network. In order to overcome bottleneck problem, network coding can be deployed in network. Network coding is a relaying architecture that combines incoming packets and forwards them. Since network coding can mitigate bottleneck problem, throughput can be improved and delay and power consumption can be reduced. In case of a single-source multicast scenario, it is known that the upper bound of multicast capacity can be achieved by linear network coding. However, in case of a multi-source multicast scenario, which is our case, finding the optimal solution is an MP hard. Therefore, in this paper, we aim to find a practical solution for network topology design with network coding in a distributed manner. We consider a large number of nodes that aim to deliver its data to their own multiple destinations. So the considered network has multi-source multicast flows. And since there is no given network topology, the connectivity between devices should be determined by each node. Lastly, we consider the most general scenario that every node can also be a source node, as in sensor networks, so all network nodes are willing to send their data toward their destination nodes. Under this scenario, we aim to determine network topology. With the given network nodes, finding network topology means determining links between nodes. Therefore, in this paper, we focus on how to determine links between nodes. In order to clearly formulate the problem, in this paper, we assume that every packet has the same size and the capacity of a link is 1 packet per unit time slot, so there is no link failure. A node can receive multiple packets based on multi-packet reception technique, and a node can transmit 1 packet per unit time slot, but multicast broadcasts are allowed. Next, let's look at the bottleneck problem in detail. For multiple sources and multiple destinations, like in this example, there are several overlapped paths. These black nodes have a bottleneck problem. since multiple incoming links are simultaneously established toward a single node. In order to avoid the bottleneck problem, the dependency between incoming links should be considered, and this is called interlink dependency. The interlink dependency condition restricts the amount of incoming packets not to exceed outgoing link capacity. In this example, V6 has 5 neighboring nodes. Here, EI60 nodes are directly linked from VI to V6. If EI6 is 1, the link is activated, and if EI is 0, the link is inactivated. So in this example, only EI6 is activated, so only EI6 is 1 and other links are 0. In order to avoid the bottleneck, node V6 should have only one incoming link, so this can be expressed as this condition, meaning that restricting the number of incoming links to at most 1. Even though interlink dependency can avoid the bottleneck problem, it becomes strict constraint, so it causes limited performance. Then, how can we solve bottleneck problem without interlink dependency? As a solution, we propose to use network coding. Since network coding can eliminate interlink dependency, bottleneck problem can be easily solved. In this example, 5 nodes are sending data to V6. Here, X160 nodes the data delivered from V1 to V6. If V6 deploy network coding, these 5 data are combined together with encoding operation and becomes the encoded data P6. Note that this is the perspective of before encoding process. However, in the perspective of after encoding, we can alternatively think that V6 received the same data P6 from all neighbor nodes. Then, V6 is now can accept multiple incoming links at the same time. Technically speaking, the incoming data become link independent, so no need to keep interlink dependency anymore. Therefore, by deploying network coding, bottleneck problem can be solved without interlink dependency. However, as I already mentioned, finding the optimal topology for network coding based multi-source multicast network is MP hard. So in this paper, our goal is to find a low complexity and practical decentralized solution with game theoretic approach. In this paper, we propose network formation game. We want to determine a set of directed links, e.g., in graph G, and find a distributed solution with a game theoretic approach. Since solving an optimization problem for a large-scale network is very complicated, we decompose the game into low-complex small games in link connections. In the proposed network formation game, there are 3 components: players, actions, and utility functions, which will be discussed in next slides. The player of a game is network nodes denoted as VI, and the action of player I is a set of decisions whether to make outgoing link or not toward the neighbor nodes. Let's look at this example. In this example, V6 has 3 neighbor nodes, V1, V2, V4. V3 builds active link toward V2 and V4 and didn't have links toward V1. Then the action of a B3 becomes a set of three links. E31 is 0, E32 is 1, E34 is 1. So in general, AI is a set of EIJ for all VJs in each neighbor. Note that the EIJ has direction from VI to VJ, and the activeness is marked as 0 and 1. The utility function of a player I is defined by reward and cost. The reward is defined as Euclidean distance reduction toward its destination nodes when the player I uses action AI. Let's look at the illustration. The player node Vi wants to deliver its data to its destination D. If the destination is located too far to be reached, so Vi cannot make a direct link to the destination, and it should use relay node. So node Vi track neighbor nodes, and there are Vk and Vj. Vj is located closer to the destination than Vk. In the other words, the distance from Vk to destination D denotes delta Kd is larger than delta Id, and it is also larger than delta Jd. In this case, which node should Vi choose as a relay node? Of course, it should choose Vj instead of Vk, because Vj is located on the way toward D, so making a link toward Vj will allow Vi to be connected to destination with higher probability. In this expression, the reward is sum of all rewards from neighbor nodes, and capital Eij returns 0 if the link between Vi and Vj is inactive, which is determined by the action AI. And Eij returns 1 if the link is active. So only when the link Eij is active, the corresponding reward is taken. So this equation means distance reduction. Here function f is an inversely proportional, so when the distances are like this, by taking function f, the direction of inequality becomes the opposite. Then, as we intended, the link toward the Vj will give positive reward, so it encourages Vi to make link Eij. On the other hand, the link toward Vk will give negative reward, so node Vi will not build the link. Therefore, the reward function is designed to allow the player correctly choose the relay node toward its destination. Next, the cost represents the link formation cost, and here we use equal division mechanism, so making a link cost lambda, which is a unit link formation cost. If both of nodes build a link toward each other, the cost is equally divided, so the cost becomes half. And if only one of them decides to make the link, that player is responsible for the cost. So far, we have defined the network formation game. By finding the optimal actions, the network connections can be determined in a distributed way, and correspondingly network topology also determined. However, in large-scale networks, the size of a player set and action set are very large, so in this case finding the solution for the game is very complicated. So next we show that our game can be decomposed into simple games with low complexity. We show that the proposed network formation game for a graph can be decomposed by network coding into independent games for edge disjoint subgraphs. Let me briefly explain key idea of proof with a simple example. In this example, there are 4 nodes in graph G, and links are determined based on the proposed game. When network coding is not used, and when the player V1 decides its link activation toward V3, it should check V2 and V4's activations because of interlink dependency. So only if the action of both V2 and V4 don't have outgoing links toward V3, V1 can build a link toward V3. But if network coding is used, interlink dependency does not need to be considered, so V1 doesn't need to check other players' action. Hence, the game for whole graph G can be decomposed into a game for subgraph Ln. If the graph can be decomposed into edge disjoint subgraphs. Since it is guaranteed to have edge disjoint subgraphs, the network formation game can be always decomposed into games for subgraphs. However, since we consider multi-source multicast scenario, V1 might have multiple destinations, so that game might not be able to simply decompose into such a way. So in order to solve the problem of multiple destination, our solution again decompose multicast flow into multiple unicast flows. In this example, the subgraph Ln has 2 subnodes, V3 and V4. In here, we propose concept of a virtual subnode. So imagine that node V3 has actually 4 virtual subnodes, and each virtual subnode has different destination. For example, V3 is a virtual subnode for destination V1, and V41 is V4's virtual subnode for destination 1. So we further decompose subgraph Ln into virtual subgraph for the same destination. Then theorem 2 can be used by decomposing multicast flows into multiple unicast flows. Finally, the network formation game can be decomposed into minimum 2-player link formation game. The proposed link formation game can be solved by finding pure stage Nash equilibrium, and it is provided in algorithm 1. We showed that at least one Nash equilibrium exists based on theorem 3. Therefore, stable network topology can be determined based on proposed link formation game. Next, based on simulation results, we see how the resulting network can be formed based on the proposed algorithm. First, we focus on network connectivity, which can be controlled by unit cost. The unit cost denotes the amount of cost to build a link. In these two simulation results, x-axis is unit cost and y-axis are total number of active links and connection failure rate. Based on these two figures, we see that as the unique cost increases, the number of active links decreases, which means less connected network is built. And this increasing connection failure rate, therefore, the connectivity of a resulting network can be controlled by unique cost. Next, we see the network utility, which is defined as sum of all rewards and costs in network. In this figure, network utility is shown for the number of nodes in network. Based on this figure, we can easily confirm that the network utility increases as network size increases. Moreover, as the unit cost decreases, network utility increases. We compare the proposed solution with three other stages. First, there are two centralized approaches. One is without network coding, so here interlink dependency should be satisfied. And the other one is with network coding, which can be the upper bound of proposed solution. Next, as a state-of-the-art distributed approach, we consider TCLE, which also determines network topology based on non-cooperative gain. In TCLE, a node chooses its transmission power by balancing the target network connectivity against transmission energy dissipation. And there is a system parameter eta, which denotes size of action set for a node. We first compare network utility. In this figure, the network utility is shown for the number of nodes in network. We can see that NC centralized with triangle marker shows the highest network utility by providing upper bound of a proposed solution, and the next highest one is proposed solution, and then third one is non-NC centralized solution because of interlink dependency, and the last one is TCLE. Here, the reason why TCLE has the lowest network utility is the focus of TCLE is on overall network connectivity in terms of algebraic connectivity, not on connection toward the destination. In this figure, we can again confirm that lower unit cost with blue color has higher network utility than red-colored high unit cost by building well-connected network. Lastly, we see the complexity to find solution. In this table, the worst-case complexity is shown for n, which denotes the number of nodes in network. So NC centralized has the highest complexity with the largest link formation choices, and the second highest one is non-NC centralized, which is still centralized solution, but interlink dependency reduce link formation choices compared to NC centralized. That's why it has lower complexity. And the third one is TCLE. And finally, the proposed solution has the lowest complexity and growth rate. In conclusion, in this paper, we propose a distributed topology design solution for multi-source multicast flows. By using network coding, we remove interlink dependency so we can solve bottleneck problem, and by using game theoretic approach, we provide a distributed solution. In the proposed solution, network nodes decide whether to make its link with neighbor nodes or not by considering reward and cost. And we show that proposed solution has low complexity by decomposing large-scale network formation gain into two-player link formation game. Thank you for your attention.